Okay. Hello, everyone. This is Group C, and we will be explaining today the interaction terms as well as nonlinearity transformations of our predictors. And so, as you can see here, we have RStudio open. The first thing that we will be doing is accounting for the additivity assumption. And the additivity assumption that we've been using this entire time with multilinearity and linear regressions is that we assume that there's no relationship between the two, or between the independent variables of our data sets. So we're going to be fixing that today, and the way we will be doing that is quite simply with this line of code. And so what's happening here is that we are having the median value of Boston houses compared with the lower status of socioeconomic status of the population, and we're multiplying that by the age. And so what we were doing before was only comparing it with LSTAT or comparing it with age individually, but we know that there's a relationship between the lower status and their age. Whenever you grow older, you're usually higher in socioeconomic status. When you're younger, you're usually lower on the LSTAT. So this will help us account for the additivity assumption and also create a relationship between the two data by multiplying their values. And so Josh now will be talking about what is the nonlinear transformations, which is accounting for the linearity assumption.
All right, so when we account for the linearity assumption, basically what we're doing is we're taking our data set, and how in the past we've kind of assumed that our dependent and independent variables have a linear relationship. That assumption does not always hold true. There's obviously going to be data out there that is going to be better suited to be fit by a function that is not just a straight linear function. And so basically this chapter that you've read about has talked about that and how to account for that. And so we are going to walk you through that a little bit through the use of this code. Like I said, you guys have read about it in the chapter, so you should have somewhat of an understanding of the purpose. So we are just going to walk you through line by line of the code and explain kind of how to do that. So to start, we're simply going to make a function in R that's going to potentially suit our data better than a linear function. And so we're going to have this first line of code, which is just making an lmfit2 like we've been doing in the past. We're going to use the median value and then the LSTAT function. But when you go through the line of code right here, you can see we square the LSTAT, which is something that we haven't done in the past. And basically what that is doing is it's going to create a parabolic function. So we can see here in a little bit whether that better suits the data than our linear function. And so I'm going to take this line of code and I'm going to run it. And then we're going to move down and run the summary of that lmfit2 that we just made. And as you see, the summary statistics show up. You guys kind of know how to navigate through that. I'm going to focus right now on just multiple R squared of about 64%. You can kind of remember that number for later, and I'll let you guys kind of navigate through some of these summary statistics. So our next step is we're going to use an ANOVA function in R to now take that parabolic function that we just made and compare it to a normal linear function like we've been doing the last few groups. And so this ANOVA function that you can see, we're just going to do ANOVA and then take our lmfit2 like we just calculated and then run an lmfit, which I just overlooked. I need to run my lmfit. That's just the linear model that we have been doing all in the past, so you guys should already have that in R. And then you compare those with the ANOVA and run that. And then if you look down at the ANOVA statistics that just came up, this residual sum of squares is a good statistic to look at for a comparison. You can see model 1 is my linear model, my linear regression, and then my model 2 is my parabolic function with my squared LSTAT. And so you can see the residual sum of squares for model 2 is lower, which is typically going to be an indicator that that is going to be a better suited for our data. And so my next line of code is going to be this par function like we've been running. I'm going to run that to set up the plot, and then I'm just going to simply plot my lmfit2. And you can see on the right side here, the residual plots came up, and with the fitted values, the fitted function to my data that is, as you can see, not completely linear. And so now that we've compared my more parabolic function with my linear function, we're going to do something a little different. Instead of just doing a squared function, we're going to create a fifth degree polynomial and see if that potentially suits our data better than just the squared function. And so what we're going to do is create another LMFIT. I call mine LMFIT 5 because we're going to go to a fifth degree polynomial. And as you can see, this one, since it's a polynomial, you don't do it to the fifth degree. You have to do the poly function and then LSTAT 5, which indicates that you want that fifth degree polynomial. So I'm going to take that line of code, run that, and then run the summary for it. And as you can see, if you remember back up in this code here, the squared, my parabolic function came back with an r squared value of about 64%. And if I scroll back down to my r squared value for our fifth degree polynomial, it shows 68%. So that can be a potential indicator that this could be a better fit for our data. And so now I'm going to run the summary with the MEDV. And now my last step that I'm going to walk you guys through is comparing the three functions that we've now talked about. So I'm going to use another ANOVA function to compare my simple linear regression, my parabolic function, and then my fifth degree polynomial using this line of code. So if I run those, then I can come down and look here at Model 1, Model 2, Model 3. As you can see, Model 1 is my simple linear regression, Model 2 is my parabolic, and Model 3 is the fifth degree polynomial. And so like we looked at earlier, you can look at the residual sum of squares. There's not a big difference between Model 2 and Model 3, but there is somewhat of an indicator that Model 3 with my fifth degree polynomial is going to be potentially better suited for our data set.
So in class on Monday, we will be doing a competition of previous data sets that we've used to see if you could use both our parabolic functions or different degrees of polynomials as well as the interaction terms to see if you can come up with a better multiple r squared to fit the previous data sets. Thank you very much.